What if I told you that a Japanese car manufacturer built a race car so revolutionary, so dominant, that racing officials basically rewrote the rulebook just to kill it? Not because it cheated. Not because it was unsafe. But because it dared to win using an engine that sounded like a banshee and burned fuel like tomorrow didn't exist. Picture this. It's June 23, 1991. The 24 Hours of Le Mans, the most prestigious endurance race on the planet. For decades, this has been European territory. Porsche, Ferrari, Mercedes, Jaguar. These manufacturers have turned this French circuit into their personal playground, with Porsche alone claiming 7 consecutive victories leading into this very moment. The crowds expect another European victory. The smart money is on the Porsches, the Mercedes, maybe the Peugeot. Nobody, and I mean nobody, is looking at the orange and green car starting from 12th position on the grid. That car is the Mazda 787B. And in exactly 24 hours, it's going to shatter everything the racing world thought it knew about endurance racing. This is legacy motoring, and I spend way too much time thinking about legendary race cars that changed motorsport forever. If you're someone who loves underdog stories, revolutionary engineering, and the moments when the little guy beats the establishment at their own game, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Here's the thing. This isn't just a story about a car winning a race. This is a story about engineers who refused to follow convention, a driver who pushed through dehydration so severe he lost 7 pounds during the race itself, and an engine design so unusual that most manufacturers had written it off as a dead end years earlier. The 787B didn't just win Le Mans. It exposed the racing establishment's greatest fear. That someone might beat them at their own game using completely different rules. And when the establishment realized what had happened, their response wasn't to congratulate Mazda. Their response was to immediately change the regulations and erase this technology from competition forever. That's the kind of story we're dealing with here today. To understand how revolutionary the 787B truly was, we need to travel back to 1961. That's when a German engineer named Felix Wankel finally perfected something that automotive engineers had been trying to crack for decades. A rotary engine that actually worked. Instead of pistons going up and down like in a conventional engine, the Wankel rotary used triangular rotors spinning in a figure-8 pattern inside an oval housing. No valves, no camshafts, no reciprocating mass. Just smooth, continuous rotation. When Mazda licensed this technology in 1967, they were the only manufacturer bold enough to bet their future on it. General Motors tested it and walked away. Mercedes-Benz tried it and gave up. Citroën built a few cars and eventually abandoned it. Even NSU, the German company that co-developed it with Wankel, eventually threw in the towel. But Mazda saw something everyone else missed. Here's what most people don't realize about the rotary engine's journey to Le Mans. By the late 1980s, Group C racing, the premier prototype class at Le Mans, was in serious trouble. Costs were spiraling completely out of control. Mercedes was reportedly spending over $100 million a year on their racing program alone. Porsche wasn't far behind. The smaller manufacturers were getting priced out of competition, and even the big players were starting to question whether the investment was actually worth it. The organizers needed a solution to control costs and attract more manufacturers back to the grid. Their answer was new regulations for 1991 that essentially turned Le Mans into a Formula One race with covered wheels. 3.5-liter naturally aspirated engines only. No more turbos. No more big displacement motors. The idea was logical enough. Manufacturers could use modified versions of their Formula One engines, spreading development costs across multiple racing programs simultaneously. Peugeot loved it. They already had a 3.5-liter V10 from their Formula One program sitting ready. Mercedes developed a new 3.5-liter V12. Jaguar brought their 3.5-liter V12. But Mazda's engineers looked at these regulations and spotted something nobody else had noticed. The regulations specified 3.5 liters for non-reciprocating piston engines. The Rotary wasn't a reciprocating piston engine. It was something else entirely. And there was a loophole sitting right there in the fine print. Calculating the displacement of a rotary engine had always been a controversial subject in motorsport. Do you count the volume of all three combustion chambers as they rotate? Do you count it once per revolution, twice? The FIA had dealt with this calculation before and used a specific formula that essentially doubled the rotary's actual displacement for equivalency purposes. Under this formula, Mazda could legally run a rotary with an actual displacement of just 2.6 liters, which would be calculated as equivalent to a 3.5-liter piston engine. But here's what the regulators fundamentally didn't understand. The rotary's greatest advantages had absolutely nothing to do with displacement numbers on paper. The heart of the 787B was the R26B engine. 4 rotors, naturally aspirated, 2.6 liters of actual displacement. Let me put those specifications in perspective for you. Each rotor housing was roughly the size of a shoebox. The entire engine was only 28 inches long and weighed just 396 pounds. That's approximately 200 pounds lighter than the Jaguar V12 they were competing against directly. The engine was so compact that Mazda's engineers could mount it lower and further forward in the chassis, giving the car a better center of gravity than virtually anything else starting on that grid. The power output was respectable but not earth-shattering at first glance. 700 horsepower at 9,000 revolutions per minute. The Mercedes C11 made 730 horsepower. The Peugeot 905 made around 650. But raw horsepower numbers weren't where the R26B was playing its most important cards. This engine's genuine party trick was its power delivery characteristic. A piston engine produces power in pulses. Explosion, exhaust, intake, compression, then repeat that cycle endlessly. Even a V12 has measurable dead spots in its power delivery curve. The R26B with its 4 rotors constantly operating in different phases of combustion delivered power like an electric motor. Smooth, linear, perfectly predictable. No power pulses, no vibration, no surging. Just a continuous, uninterrupted flow of thrust that drivers could exploit with remarkable precision on every single corner exit. So when you think about what that actually means at race pace over 24 hours, you start to understand why Mazda was genuinely dangerous. The engine internals were a masterclass in endurance engineering philosophy. The rotor housings were chrome-plated for wear resistance that would last the full race distance, and then some. The apex seals, traditionally the rotary's well-documented weak point, were manufactured from a carbon composite material that Mazda had been quietly refining since the early 1970s. 2 decades of incremental development had turned the rotary's greatest liability into one of its most reliable components. The eccentric shaft, essentially the rotary equivalent of a crankshaft, was forged from a special steel alloy specifically engineered to handle continuous high-speed rotation for 24 straight hours without fatigue failure. But the real genius in the R26B was buried in its peripheral port induction system. Instead of intake ports located in the side housings like a conventional street rotary engine, the R26B had ports directly in the rotor housing periphery itself. This meant the incoming air charge didn't have to make any sharp directional turns before entering the combustion chamber. Air flowed straight in, following the path of least resistance. The result was better volumetric efficiency, higher RPM capability, and that absolutely distinctive howl that sounded like nothing else anywhere on the racing circuit. Let me explain what that actually meant in practice for anyone standing trackside at Le Mans in 1991. When a 787B flew past you at 200 miles per hour on the Mulsanne Straight, you didn't hear the typical racing engine scream that spectators had become accustomed to over decades. You heard something that sounded like a cross between a Formula One car and a jet turbine spinning up for takeoff. A smooth, continuous wail that climbed and climbed without the typical shift points and power interruptions you'd hear from any piston engine. Spectators reported that you could identify a 787B with your eyes completely closed from a mile away. That sound became the car's signature, its calling card, and ultimately one of the most beloved sounds in motorsport history. Now, you might be thinking that Mazda just showed up at Le Mans with this radical engine and hoped for the best. Look, nothing could be further from the truth. They had been developing rotary technology in competition for nearly a decade before that 1991 victory. The 757 and 767B predecessors had shown genuine promise, but lacked the reliability needed for a 24-hour race. Mazda's engineers spent 3 years methodically analyzing every single failure, every weakness, every component that had let them down in previous campaigns. They tested components on specialized rigs that simulated 24 hours of racing loads compressed into shorter time frames. They ran complete engines continuously for 48 hours straight, then tore them down completely, examined every internal part under electron microscopes, identified microscopic stress points invisible to the naked eye, and rebuilt them stronger each time. The chassis itself reflected this philosophy of measured evolution rather than revolution. Designed by Nigel Stroud, who had previously worked on March Formula One cars, it was a carbon fiber monocoque that deliberately prioritized reliability over ultimate outright performance. The suspension used conventional double wishbones with push-rod-actuated springs and dampers. Nothing exotic, nothing clever that could fail at 3 a.m. with the race lead at stake. The Dunlop tires were specifically developed around the car's unique weight distribution and power delivery characteristics, optimized not for a single hot lap but for consistent degradation curves across a full race stint. The aerodynamics told a similar story of deliberate restraint. The 787B produced approximately 1,300 pounds of downforce at 200 miles per hour. Decent, but genuinely not exceptional by the standards of that field. The Mercedes C11 generated significantly more. The Peugeot 905 was actually slipperier through the air in terms of drag efficiency. But Mazda's engineers had absorbed a painful lesson from their years of Le Mans heartbreak. The fastest car almost never wins a 24-hour race. The car that breaks the least wins Le Mans. That insight drove every single design decision in the 787B program. This is where it gets really interesting when you look at the driver lineup Mazda assembled for their 3-car assault on Le Mans that year. The lead car, chassis number 55, received Johnny Herbert, Bertrand Gachet, and Volker Weidler. Herbert was a Formula One driver, yes, but not a frontrunner at that point in his career. Gachet was quick but widely regarded as erratic under pressure. Weidler was a sports car specialist without the headline name recognition of the factory Mercedes and Jaguar pilot. On paper, this wasn't an intimidating lineup. The rival factories had assembled rosters of proven winners specifically to dominate this race. But Mazda had done their homework carefully. They didn't need the absolute fastest drivers. They needed supremely consistent drivers who could adapt specifically to the Rotary's unique operating characteristic. The R26B's power delivery was so fundamentally different from any piston engine that drivers genuinely needed to recalibrate their entire driving approach from scratch. Brake points were different because the car decelerated differently. Corner exit speeds were consistently higher because the power came on so smoothly and progressively. The car didn't lose momentum between gear changes the way piston-engined competitors did, because the power delivery never truly interrupted. Here's something that wasn't public knowledge at the time and took years to fully emerge. Mazda's engineers had programmed the engine management system with multiple distinct maps for different conditions and driver requirement. Map 1 was full attack mode, delivering all 700 horsepower with maximum fuel consumption. Map 2 dialed back to approximately 650 horsepower for meaningfully better fuel economy during stable traffic phases. Map 3 was pure survival mode, restricted to around 600 horsepower, but the engine could run lean enough to extend stint lengths by almost 20 full minutes compared to Map 1. The drivers could switch between these maps on the fly using a rotary dial mounted directly on the steering wheel, giving them strategic flexibility that competitors simply didn't have access to. On race day, June 22, 1991, the weather conditions were perfect. Warm, dry, with a light breeze drifting across the circuit. The Peugeot had dominated qualifying entirely, with the 905 of Alain Cudini sitting on pole position. The Mercedes entries looked frighteningly strong throughout practice. The Jaguars had the raw speed to threaten everyone on their best lap. The three Mazda 787BS had qualified 12th, 19th, and 23rd on the grid. Not exactly the starting positions that inspire confidence heading into the biggest race of the year. When the flag dropped at 4 in the afternoon, the Peugeot immediately pulled away from the field. The Mercedes C11 of a young driver named Michael Schumacher, yes, that Michael Schumacher, charged aggressively through the midfield. The Jaguars were fast but fragile as their reputation suggested, and the Mazdas simply circulated. Steadily, consistently, lap after lap after lap, hour after hour without drama. By midnight, the race had already claimed several high-profile victims. One of the Peugeots had retired with engine failure. A Mercedes had crashed heavily. Two of the Jaguars were already parked in the garage with various mechanical gremlins. The number 55 Mazda had climbed quietly to 6th place, not through blazing speed, but through the simple, unglamorous virtue of persistent mechanical reliability. They were lapping approximately 2 seconds slower than the leaders on comparable fuel loads, but they weren't stopping nearly as frequently for fuel replenishment. Here's where the Rotary's efficiency equation became genuinely decisive in the overall strategic picture. Yes, the R26B consumed fuel at a rate of roughly 3.5 miles per gallon at race pace, which sounds terrible in isolation. But because the entire engine package weighed so much less than the V12 competitors, Mazda could fit a larger fuel tank without exceeding the minimum weight limit. The 787B carried 32 gallons of fuel versus the 28 gallons in most of its direct competitors. Combined with the ability to run the lean map during stable phases of the race, the Mazda could sustain racing for almost a full hour between mandatory fuel stops, while the Mercedes and Jaguars were returning to the pits every 45 minutes regardless of their own strategies. Let that calculation sink in properly for a moment. Over a full 24-hour race, those additional 15 minutes per stint meant the Mazda made approximately 6 fewer pit stops than its primary competitors. At roughly 50 seconds per stop including the actual service time and the pit lane speed limit sections, that translates to 5 full minutes of race time saved purely from not standing stationary in the pit lane. 5 minutes that the Mercedes and Jaguar drivers had to earn back through raw lap time that simply wasn't there consistently. The real advantage, though, the one that separated genuine strategy from pure luck, came in the dead of night between 2 in the morning and 4 in the morning, when accumulated driver fatigue peaks and mistakes begin multiplying exponentially across the entire field. This is when the 787B's smooth, forgiving power delivery became an almost unfair competitive asset. Johnny Herbert described it later in interviews, and his words have stuck with motorsport historians ever since. He said that in the dark, when you're exhausted and your reactions are measurably slower, the Mazda was so fundamentally forgiving that it allowed you to drive beyond your physical state. No sudden power surges to manage, no wheel spin events to catch, no moment where the car would punish a slightly mistimed throttle application. It just pulled cleanly, predictably, reassuringly out of every single corner regardless of what your tired body was asking of it. By dawn on Sunday morning, the number 55 Mazda sat in 4th position overall. The leading Mercedes had developed gearbox problems and was bleeding time on every pit visit. The remaining Peugeot was screamingly fast but consuming its tires at an alarming rate, the unavoidable price of generating that much aerodynamic downforce across 24 hours of racing. The Jaguar of Teo Fabi was running at the front, but experienced observers in the paddock were quietly waiting for the inevitable mechanical failure that Jaguar endurance campaigns had become known for producing at the worst possible moments. At 8 in the morning, with 8 hours remaining on the clock, Mazda made the crucial strategic call that would define the race. They put Volker Weidler in the car with clear instructions to push harder than they had been running throughout the night. Not flat out by any means, but meaningfully harder than the conservative pace they had maintained. Map 1 instead of Map 2. The engineers had run their calculations carefully and determined they had sufficient engine life remaining to absorb the increased pace without risking a mechanical failure in the final hours. The fuel numbers still worked if they managed stint lengths carefully. The gamble paid off almost immediately. Weidler started turning laps consistently 2 full seconds faster than the pace they had been running. When the leading Jaguar inevitably expired with an engine failure just before noon, the exact outcome the paddock had been quietly predicting, the Mazda inherited second position overall. Only the Mercedes of Johann Mass stood between them and a victory that nobody outside the Mazda garage had considered remotely possible at the start of the previous afternoon. Then, with 3 hours remaining, the Mercedes developed a mysterious misfire that the team simply could not diagnose or fix. They changed spark plugs on the next stop. They checked fuel pressure readings. They swapped ignition modules. Nothing restored the engine to full health. The mighty V12 was dying on the circuit, and the engineers monitoring the data back in the garage couldn't identify the root cause with enough confidence to prescribe a definitive solution. Every single time the Mercedes powered down the Mulsanne straight, the gap to the Mazda behind it shrank measurably. The mathematics of the situation were becoming undeniable. Then Johnny Herbert took over the 787B for the final stint. His instructions from the team principal were deliberately simple and direct. Bring it home. Don't take unnecessary risk. Don't try to be a hero. The car had been running continuously for 21 hours without a single mechanical issue of any significance. Engine temperature remained stable and within normal parameters. Oil pressure was reading perfectly. Even the brake pads had been measured and confirmed to have sufficient material remaining to complete the final 3 hours without a change. But here's what the television coverage of that afternoon simply didn't capture or communicate to the watching audience. Herbert was in genuine serious physical distress inside that cockpit. The 787B's interior temperatures reached 140 degrees Fahrenheit during the peak heat of the day, with the carbon fiber tub acting as a remarkably efficient oven baking the driver from every direction simultaneously. Herbert had already lost 7 pounds of water weight across his previous stints in the car. His vision was beginning to blur at the edges from dehydration. His hands were cramping around the steering wheel. The team was radioing him on every single lap to confirm he was still functioning adequately, and Herbert's response to their concerned calls became legendary within Mazda's racing history. He told them, through a voice that those who heard it described as surprisingly calm and completely determined, that he didn't care what physical state he was in. We're finishing this race in first place. At 3:47 in the afternoon on June 23rd, after precisely 24 hours of continuous racing, the impossible happened. The orange and green Mazda 787B, with its weird engine that sounded like a vacuum cleaner had somehow mated with a jet turbine, crossed the finish line in first position. They had completed 362 laps covering 3,262 miles at an average speed of 127 miles per hour across the full 24-hour duration. The rotary engine, the technology that virtually every expert in motorsport had said would never survive 24 hours of sustained race pace, had run absolutely flawlessly from the opening flag to the checkered flag. It was the first time a Japanese manufacturer had ever won Le Mans. It was the first victory for a rotary engine in the history of the race. And as the world would discover quite quickly, it would also be the last. Here's the part of this story that most people who know the headline result have never fully explored. Within hours of Mazda taking their victory lap, the rumblings had already started in the paddock. The European manufacturers were not pleased with what had happened, and they made their displeasure known through the channels available to them. Peugeot filed a formal protest questioning the Rotary's displacement calculation methodology. Mercedes raised questions about the fuel flow measurements recorded during the race. Jaguar wanted the car's weight rechecked against the minimum regulations. Every single protest was examined and dismissed. The 787B was found to be completely and unambiguously legal in every measurable respect. But the damage to the establishment's comfortable assumptions had already been done. The FIA, the governing body of international motorsport, suddenly and conveniently announced that for the 1992 season, the technical regulations would be revised once more. Only 3.5-liter piston engines would be permitted going forward. No rotaries allowed, no exceptions made, no grandfather clauses for existing machinery. The official justification offered publicly was the promotion of closer competition and better cost control across the grid. The real reason, understood by everyone in the paddock but spoken about carefully, was straightforward political protection of massive prior investment. The European manufacturers had spent hundreds of millions of dollars collectively developing their piston engine programs. They had committed financially to this technical formula and built their entire racing strategies around it. And here came Mazda, spending a fraction of those budgets, using a completely different engineering approach, and embarrassing the entire establishment at the sport's most prestigious event. It wasn't simply that Mazda won the race. Any competitor can have a good day. It was that they won using an approach that made everyone else's enormous financial investment look strategically questionable. Think about it from Peugeot's specific perspective for a moment. They had developed a complex, expensive, precision-engineered V10 requiring exotic manufacturing processes and constant development attention. Mazda had one using an engine design concept dating from the early 1960s that was fundamentally built around triangular rotors spinning in circles. The humiliation extended beyond the sporting result and into the engineering philosophy itself. And the R26B was immediately banned from top-level competition without delay. Now, you might be thinking that banning a technology that just proved its superiority sounds like exactly the kind of corporate politics that ruins sport. And you wouldn't be wrong to think that. Mazda protested the decision formally and argued their case through available channels. They had spent years developing this specific technology precisely for these exact regulations. They had a full 2-year development program planned with an evolved 787C already in the early stages of development. The R26B still had substantial untapped performance potential sitting in it. The engineers had conservatively estimated another 50 horsepower was achievable with continued development time, better understanding of the peripheral port geometry, and optimization of the engine management mapping. But the decision from the FIA was final, unappealable, and immediately implemented. What makes the banning even more difficult to accept when you examine the complete picture is what happened to Group C racing after the Rotary was eliminated. The 3.5-liter formula that was presented as the solution to the sport's problems failed comprehensively and quickly. By 1993, the majority of major manufacturers had abandoned prototype racing programs entirely. The racing grid shrank dramatically from what it had been in the competitive years. The racing became increasingly processional with fewer genuine competitive battles for the overall lead. Le Mans entries dropped from 55 cars in 1991 to just 47 in 1993, and the decline continued from there. The medicine administered by the FIA turned out to be considerably more damaging than the disease they claimed to be treating. By attempting to control costs and standardize the technical approach, they inadvertently destroyed the competitive diversity that had made the category compelling to manufacturers and spectators alike. The 787B itself became a museum piece in the most literal sense possible. Mazda retained chassis number 55, the actual winning car, and it now resides permanently in the Mazda Museum in Hiroshima as the centerpiece of the company's motorsport heritage display. But here's something genuinely remarkable about that car's ongoing relationship with its original engine. Mazda still starts it up regularly. Not as a static display piece, not as a carefully preserved artifact too fragile to disturb. They run it. The same R26B engine that won Le Mans in 1991 still fires up on command, still produces that completely distinctive multilayered howl that made spectators stop whatever they were doing in 1991, still runs as smoothly and as confidently as it did on that June afternoon. The other chassis from that campaign have taken different paths through history. Number 18 resides in a private collection in Japan. Number 56 makes occasional appearances at prestigious historic racing events where, remarkably, it remains genuinely competitive against cars built many years after it was designed. When the 787B runs at events like the Goodwood Festival of Speed or the Monterey Historic Races, crowds abandon whatever else they were watching and gather specifically to witness and hear this car in motion. Photographers who have covered motorsport for decades describe trying to capture something about it that goes beyond its visual appearance. There's a presence to it that still photographs simply cannot communicate. And then it fires the engine, and the sound does the communicating that images never could. That smooth, climbing, continuous wail that sounds like nothing produced before or since in motorsport history. It cuts through ambient crowd noise effortlessly. It makes people turn their heads involuntarily. It creates an immediate and instinctive physical reaction in anyone within earshot. The technical legacy of the 787B extends considerably further than that single famous victory in the French countryside. The peripheral port technology specifically developed for the R26B directly influenced Mazda's production rotary engines for the following 2 decades of street car development. The carbon apex seals refined through the racing program became standard components in later RX-7 and RX-8 powertrains, meaningfully improving their durability and refinement over the purely metallic seals used in earlier generations. The variable engine mapping concept that Mazda pioneered and deployed in the 787B during the 1991 season predated similar driver-adjustable engine management systems in Formula One by several years. Technology that was considered exotic and specialized in a Le Mans prototype quietly filtered down into road cars and then into the broader motorsport ecosystem. But the most significant and durable legacy of the 787B isn't found in any specific technical component or engineering solution. It's found in what the car's complete story represents as a philosophical statement about engineering problem solving. In a world populated entirely by V12S and V10S, all following essentially the same fundamental technical template that hadn't changed in its core principles since the 1890s, Mazda chose to be genuinely different. They took a technology that the entire global automotive industry had examined, tested, and then collectively abandoned as impractical. And rather than accepting that collective verdict, they continued refining it patiently, methodically, relentlessly across 2 decades until it was perfected. And when the R26B produced 269 horsepower per liter, which was genuinely exceptional for a naturally aspirated engine in 1991, it achieved this while simultaneously being lighter, more compact, and inherently smoother in its operation than any piston engine on the Le Mans grid that year. The fact that it was banned from competition immediately after winning the race tells you everything meaningful you need to know about how genuinely threatening this technology was to the established order's sense of security and competitive certainty. The establishment could accept being beaten by a competitor using the same basic approach. What they couldn't accept was being beaten by someone who had looked at the entire accepted framework and concluded that a fundamentally different answer existed. Consider for a moment the complete engineering philosophy embedded in every aspect of the 787B. Every single design decision made throughout the program prioritized the performance of the complete system over the maximum individual performance of any single component. The engine wasn't the most powerful unit on the grid, but it was by far the lightest and most packaging-friendly. The aerodynamics weren't the most aggressive downforce-generating solution available, but they balanced aerodynamic efficiency with consistent, predictable tire behavior across full stint distances. The chassis wasn't the most technically advanced structure the engineering team could have built, but it was extraordinarily reliable over distances and timescales that exposed the limitations of more ambitious designs. This systems-level thinking, the practice of optimizing the entire car as an integrated whole rather than chasing maximum specification in each individual area separately, was genuinely revolutionary in an era when most racing teams approached development by asking how much more of everything they could add. The drivers who raced the 787B across its competition career still speak about it with a reverence that time hasn't diminished. Johnny Herbert, in numerous interviews conducted years after the Le Mans victory, consistently called it the most perfectly balanced racing car he had the privilege of driving across his entire career. Volker Weidler described the power delivery in terms that automotive engineers still find technically interesting today. He said you could place the car anywhere on the circuit you wanted using the throttle alone, with a precision and repeatability that no piston engine car he had driven could match. Bertrand Gachet, whose post-Le Mans career took some turbulent turns unrelated to his driving ability, still described the R26B as simply indestructible in his experience of it. You could push it against its limits repeatedly, he said, and it would simply continue singing. The mechanics and engineers who worked directly on the car throughout the campaign tell stories that complement the driver testimony from a completely different perspective. Unlike piston engines that demand constant technical attention between stints and sessions, valve adjustments, cam timing verification, piston ring condition checks, the R26B required relatively straightforward attention to fluid levels and basic system check. One senior mechanic from the 1991 team recalled the moment after the Le Mans victory when they disassembled the race-winning engine, expecting to find the evidence of 24 hours of abuse written across every internal surface. What they found instead was components that appeared nearly new in their condition. The rotor housings showed minimal where that was well within acceptable parameters. The carbon apex seals retained significant remaining service life. The eccentric shaft bearings were in essentially perfect condition. The engine had been run to winning pace across a full 24-hour race, and it looked like it could have done it again. This level of retained condition after 24 hours of sustained race pace wasn't accidental, and it absolutely wasn't luck. Mazda's engineering team had learned through painful experience across years of rotary development that the genuine key to endurance reliability wasn't adding structural strength to components approaching their design limit. The key was systematically removing stress from components so they operated well within those limits. Every single component in the R26B was designed and specified to operate at approximately 70% of its theoretical maximum capability under race conditions. While competitor teams were pushing exotic materials right up to their structural limits in the pursuit of additional horsepower or reduced weight, Mazda had deliberately built enormous engineering safety margins into every part of the drivetrain. This philosophy cost them some outright performance potential, but it bought them something far more valuable in the context of a 24-hour race. The fuel system illustrates this overbuilding philosophy with particular clarity. The R26B used 3 completely separate fuel pumps, 1 primary unit and 2 independent backups operating in parallel. If the primary pump failed at any point during the race, either of the backup systems could maintain full fuel pressure without any action required from the driver or pit crew. The fuel injection system used redundant sensors for every critical operating parameter monitored by the engine management computer. If any individual sensor failed or produced a reading outside expected parameters, the management system would instantly switch to backup values calculated from other available sensor inputs rather than defaulting to a conservative protective mode that would cost lap time. The car was engineered to absorb multiple simultaneous component failures and still complete the race. The cooling system reflected identical thinking. 3 separate radiators, one mounted in the nose of the car and one in each side pod, 2 independent oil coolers, 3 separately controlled cooling fans. The combined cooling capacity of this system could dissipate almost twice the thermal load that the R26B actually produced at maximum race pace. During the entire 24-hour race, the engine's oil temperature never exceeded 195 degrees Fahrenheit, while competitors were regularly observing readings of 220 degrees or higher and managing their pace accordingly to protect their powertrains. The Mazda team spent their race managing strategy and tire degradation. Their competitors spent significant mental energy managing engine temperatures. The exhaust system deserves specific mention because it addresses one of the Rotary's most demanding engineering challenges. The 4-rotor configuration produced exhaust gas temperatures that could exceed 2,800 degrees Fahrenheit under sustained high-load operation. Managing that thermal energy safely over 24 hours required solutions borrowed directly from aerospace engineering rather than conventional motorsport practice. The exhaust manifold was fabricated from Inconel, a nickel-chromium superalloy developed originally for jet engine turbine sections and rocket motor components because of its ability to retain structural integrity at temperatures that would destroy conventional stainless steel. The manifold was wrapped in ceramic fiber insulation, surrounded by reflective heat shields, and provided with dedicated cooling airflow ducts specifically to the exhaust system. After 24 hours of operation that included sustained periods at full throttle on the Mulsanne straight, the exhaust system showed no cracks, no thermal warping, and no measurable degradation in any component. The aerospace-grade materials had done their job completely. The gearbox selection tells another important story about the philosophy driving every decision in the 787B program. While competitors were deploying exotic sequential transmission systems with sophisticated electronic control systems and bespoke internal components, Mazda chose a modified version of the Porsche 962's proven transmission. This unit had accumulated thousands of competitive racing miles across multiple seasons in Porsche's own hands, building a reliability record that no newly developed gearbox could match. It wasn't the lightest available option. It wasn't the fastest shifting unit on the market, but it was bulletproof in a way that newly developed systems simply couldn't claim to be without the accumulated evidence of competition experience. The synchromesh components were deliberately oversized beyond what the application strictly required. The gear sets were shot-peened, a process that induces beneficial compressive stresses in the surface layer of the metal to improve fatigue resistance under cyclic loading. The lubrication and cooling systems were, consistent with every other element of the car, considerably more capable than the minimum necessary to protect the gearbox in normal operation. It shifted cleanly, precisely, and with identical feel on lap 1 as it did on lap 362. And now, because it's impossible to discuss the 787B completely without addressing it directly, let's talk properly about that sound. The sound that made Le Mans spectators stop walking, turn their heads, and stand still trying to understand what they were hearing. The R26B's exhaust note peaked at 138 decibels at full throttle operation, a figure roughly comparable to a jet aircraft taking off 200 feet from your position. But it wasn't simply the volume that made it distinctive and immediately recognizable over a field of 30 other racing cars, all producing their own considerable noise. The frequency profile of the Rotary's exhaust was genuinely unique in the competitive landscape. The fundamental tone sat at approximately 600 Hz, with harmonic overtones extending continuously up to 15,000 Hz. Piston engines produce their characteristic sound as a sequence of discrete combustion events, each individual cylinder firing creating an audible pulse in the exhaust note. Even the smoothest V12 produces 12 discrete pulses per crankshaft revolution, and trained ears can hear that rhythmic, staccato quality in the sound. The R26B's continuous combustion cycle produced a pure, uninterrupted tone that climbed mathematically with engine RPM, like a single musical instrument rather than a mechanical percussion ensemble. It sounded, as many people who heard it have struggled to articulate properly, like it came from the future. The psychological effect of this sound on competitors who were being overtaken by the 787B was something that came out in various driver interviews and accounts collected years after the race. Being passed by the Mazda was described by multiple competitors as uniquely unsettling. The smooth turbine-like wail would grow in volume from behind as the car closed the gap, maintain that same eerily consistent tone through whatever corner the pass occurred in, and then gradually recede in pitch and volume as it pulled away into the distance. No gear change interruptions in the sound. No moment where the power delivery hesitated and gave you a competitive opportunity. Just that climbing, fading note that told you with complete clarity that something fundamentally different from everything else on circuit had just gone by. Here's what most people don't realize about the broader implications of what happened after that victory. The banning of the rotary engine from Le Mans wasn't simply about one car or one engine configuration. It was about the message that decision sent to engineering innovation throughout the sport. The FIA's choice communicated something clear and unambiguous to every manufacturer's engineering department. Conform to the accepted template or face exclusion. Find a creative and legitimate interpretation of the regulations that gives you a genuine competitive advantage, and those regulations will be rewritten to eliminate your advantage. Don't embarrass the established players with unconventional solutions that make their massive investments look strategically questionable. This pattern has appeared repeatedly throughout motorsport history, and the 787B was simply its most egregious and most consequential example. Active suspension was banned from Formula One not for safety reasons but for being too effective. Blown diffusers were outlawed when they proved too advantageous. Mass dampers were prohibited specifically when Renault demonstrated their effectiveness. The list continues because the pattern repeats. The rotary engine story in production cars continued for another 2 decades after Le Mans, eventually ending not through regulatory action but through the mounting pressure of global emissions legislation and fuel economy standards that the rotary's fundamental operating characteristics made increasingly difficult to meet. The last RX-8 rolled off Mazda's Hiroshima assembly line in 2012, ending 45 years of continuous rotary production car development that had begun with that audacious decision to license the Wankel technology in 1967, when every other manufacturer had already concluded it wasn't worth pursuing. But Mazda never fully abandoned the rotary concept, even after that production car line ended. Their research and development teams continued working with the technology in parallel with their mainstream powertrain programs, filing patents for new rotor geometries, improved sealing systems, and alternative combustion approaches that addressed the fuel economy and emissions weaknesses that had proven fatal to the RX-8's commercial viability. In 2023, that ongoing work finally produced a road car application that Mazda believed could survive in the modern regulatory environment. The MX-30 REV compact SUV uses a small single-rotor engine not as a primary drive source but as a generator for a plug-in hybrid electric drivetrain, functioning essentially as a highly compact, smooth-running range extender that eliminates the range anxiety associated with pure battery electric vehicles while leveraging the rotary's specific advantages in a context that works around its traditional weaknesses. It is emphatically not the fire-breathing racing application that made the R26B legendary. No one watching it charge a battery pack will mistake the experience for Le Mans. But it proves something important about engineering honesty. The Rotary's genuine advantages, its extraordinary compactness relative to its output, its mechanical smoothness arising from the absence of reciprocating mass, and its remarkably small number of moving parts compared to any equivalent piston engine, those advantages remain real and exploitable in 2023 just as they were real and exploitable in 1991. The technology itself was never the problem. Finding the right application for its specific characteristics was always the challenge. What the 787B ultimately proved, and what its story continues to prove to anyone who follows motorsport and engineering history carefully, is that the definition of the best solution to an engineering problem is not fixed or universal. It depends entirely on the specific constraints, priorities, and performance requirements of the complete system you're trying to optimize. In a racing environment that rewarded absolute peak lap time above all other considerations, the Rotary's advantages in power delivery smoothness and packaging efficiency were interesting but not necessarily decisive. In a 24-hour endurance race where reliability, fuel strategy, driver fatigue management, and mechanical consistency across extreme time and distance were the actual determining factors of competitive outcome, those same characteristics became exactly what was needed to win. Mazda understood their problem better than their competitors understood it. They optimized for the actual challenge rather than the most visible one. And they won. The drivers, the engineers, and the mechanics who were part of that 1991 Sierra Leone's Man's campaign have described in various retrospective accounts the atmosphere inside the Mazda garage during those final hours of the race. As it became increasingly clear that the car was genuinely going to win, that the mechanical reliability they had built so carefully across years of preparation was going to hold through to the finish, the emotional weight of the moment was almost overwhelming for people who had invested professionally and personally in this program for years. These were engineers who had heard repeatedly that the Rotary engine was a dead end, that it would never be reliable enough for 24-hour racing, that Mazda should abandon the technology and build something conventional. Every lap that number 55 completed in those final hours was a direct refutation of that received wisdom. Every pit stop that contained nothing more than fuel and a driver change was evidence that the years of patient, methodical development work had produced exactly what it was designed to produce. Johnny Herbert crossing that finish line in first position, physically depleted but completely focused, represents something beyond a sporting achievement in the context of engineering and innovation history. It represents the vindication of a development philosophy that prioritized understanding over imitation, that valued systematic preparation over reactive improvisation, and that chose to optimize the complete system rather than maximize any single impressive specification. The 787B didn't win Le Mans because it was the most powerful car. It didn't win because it had the most sophisticated aerodynamics or the most advanced electronics or the highest profile driver lineup. It won because every decision made throughout its conception, design, development, and race strategy was made in service of the actual objective rather than the superficially impressive metrics that tend to attract attention and resources in competitive environments. The establishment's response to that victory revealed something unflattering about the culture of international motorsport that observers and historians have been discussing ever since. When innovation genuinely threatens established interests, the response too often isn't to improve and compete but to regulate and exclude. This isn't unique to motorsport, and it isn't unique to 1991. But the Mazda 787B's story makes the dynamic unusually visible because the timeline is so compressed and the documentary evidence so clear. Car wins race. Car is immediately banned. Official justification offered. Real motivation understood. And the sport that banned the innovation quietly declines in the years that follow. The 787B won Le Mans exactly once. It was then immediately excluded from future competition. Its technology was outlawed through regulatory changes implemented with remarkable speed. Its further development was terminated before the potential that Mazda's engineers had identified could be explored. But in that single, complete, extraordinary 24-hour performance, it achieved something that no subsequent regulatory decision could retroactively remove. It proved that David still beats Goliath sometimes. It proved that patient, systematic, methodical development of an unconventional approach can produce results that dwarf the output of vastly greater resources applied to the conventional solution. It proved that the engineers willing to continue working on something that the consensus has already written off, the ones still refining and testing and improving while everyone else has moved on to the accepted answer, those engineers occasionally produce something that changes what everyone thought was possible. So the next time someone tells you that the obvious solution is the only solution, the next time conventional wisdom presents itself as settled fact, the next time the establishment explains confidently that certain approaches have been tried and found wanting, remember those 4 spinning triangles that conquered Le Mans. Remember the orange and green car that started 12th and finished first. Remember the engine that sounded like nothing else in motorsport history and ran for 24 hours without a mechanical complaint. And remember that sometimes the rule book gets rewritten not because you were wrong, but because you were so completely, demonstrably, embarrassingly right that the only available response was to change the rules. What do you think? Was banning the Rotary the right decision for the sport? Or did Le Mans lose something genuinely irreplaceable when they outlawed this technology? The comments are right below, and I read every single one. If you want more stories about legendary engineering that changed what we thought was possible, subscribe to Legacy Motoring and join a community of people who believe the best automotive stories haven't been told often enough. Until next time, keep questioning the conventional answer. I'll see you in the next one.